Basically, what this heat pump thing is all about, it is the reuse of waste heat. There's no point in just generating a lot of new heat with your gas burners or whatever if you already have a heat source. And that 40-degree water here contains quite a lot of energy and it is just waste. And instead of just blowing it away and having a furnace heat up your building, then we can take that heat with the heat pump and convert it into a higher state of energy, so a higher temperature of water, return it to the building and heat it up. And we can do that for a very low cost, because every time we use 1 kilowatt for running the heat pump, we get somewhere between 2.5 and 3.5 kilowatts of heat out of it. So
And
that's
what
not
we
a bad deal. But with
and,
today's gas prices and electricity prices, that's not a bad deal.
yeah, the thing is that we've done this in refrigeration for years. We just had the condensers out, and they're out there now, just throwing all that heat away. We're just throwing it to the atmosphere. We're creating heat energy because we got to push that unit up over the condensing point, push it really high, and then we just reject the heat. So we pull the heat out of the product and reject it. Then we came in with heat reclaim, where you said earlier we got heat recovery, heat reclaim. Now we heat up preheat water or preheat air in the building. But now even bigger in that, on bigger process, now we're using these heat pumps to actually take a lot of that heat and then heating these buildings, because I'm seeing more and more of this happening with CO2, a full all-in-one system. Welcome to another CO2 Experts Live. Super excited about this session. Hanging out with my good friend Erik Holland. We were hanging out earlier in August. Super great conversation about CO2. This guy's an expert in CO2. He's been doing it for decades, and he's been in the field. So from the manufacturer, learning how to set it up and design it and engineer it, to out in the field doing the startups. And the latest systems he's working on is CO2 heat pumps. And I'm super excited to dive in this. So if you have any questions, put it in the chat. If you're listening on the podcast, send some comments in, because we really want to grow your knowledge here. Erik, welcome to CO2 Experts. How you doing, brother?
Thank you, Trevor. I'm good. Always a pleasure to talk with you. Yeah, it's a nice day for talking about some CO2 business here. We talking about all this heat pumps and starting up and everything, but maybe I should just start by telling everybody who I am.
Yeah.
I work for Advancer. I'm currently in the after sales service department, where I pick up phone calls for customers and try to help them out with the systems, and we help them start up our systems and troubleshooting and making things work out in the field, basically. So, and yeah, part of that is also to help the customers commissioning and train the customers in using the racks, and especially training them in CO2 in general. So at the moment, I'm sitting here in our training facility. We got a rack here behind me. We can play with all the students, and we can teach them how things work. So that's super great.
Yeah. For those who don't know Erik, he was instrumental in the transition with Hillphoenix. He came over, he worked with the team down here in Atlanta for a long time on the control system. Back in when was that? Back in 2011, 2010?
That was back, yeah.
Yeah. So all the equipment that you're working on, if you work on any Hillphoenix here, CO2 or Advancer, Erik was a big part with Scott Martin and the team down there working together to develop the North American CO2 system. So this guy knows his stuff on CO2. So I'm super excited to get into the CO2 heat pumps, because this is something that it's not new, but it's continually starting to grow because of electrification. And this is important for contractors and technicians to know, because when they start to see more and more of it, there's some differences versus the HFC heat pumps they would have seen in the past.
Yeah, it's a new thing. It's a new thing as an old thing. We have known for a long time. We basically just called it heat reclaim systems. But the primary function there was not the heating part, that was the cooling part. But now the market is moving a bit, so now it's becoming interesting to make bigger units which are dedicated for heating, either for just locally heating your factory, or heating your community, or your big hotel facility resort, and whatever you have. So now the market has shifted a bit. So now we have dedicated control equipment and hardware to do the heat pumps.
Yeah. And this is what's exciting about CO2 because it's starting to change. We know, and I talked about it many times on our CO2 shows, is that CO2 is one of the best heat transfer refrigerant. There's a lot of heat in CO2. And when you utilize it properly, you can get warmer or hotter temperatures than older HFC refrigerants. Is that correct, Erik?
That is, yeah, for the old refrigerants, you usually ammonia. You can get a lot of heat of ammonia, but you get it in a different way and from different heat sources. But when we're talking like distributed heating systems and everything, the return temperatures and delivery temperatures are a bit different. So we need some different equipment. Here in this segment, CO2 is quite good and can deliver quite hot water to your city or to your factory. The new system we make can make up to 95 degrees water outlet from it. So you can,
wow.
that will be
That's
your
200, over 200.
almost 200 degrees Fahrenheit. Yeah.
Yeah.
So we can deliver an enormous amount of heat from whatever heat source you got. So that could be either we heat the return water from the distributed heating system, or you can have a heat source just like a normal air-to-air heat pump, from your home installations. Or it could be interesting things like exploring heat sources like waste heat from factories, or waste heat from water treatment plants, or for biogas reactors. So all the waste heat from that, you can extract that heat and put into your heat pump and use it for distributed heating or production heating or whatever you need.
Yeah. So there's a lot of applications, and we're going to see more and more of this. And so you have been to multiple startups. You like I talked with the team when I was at Chelventa. You've been working with the team, you've been learning about it, but you're actually out in the field with the contractors. What is the difference between your startup of a CO2 transcritical booster rack to now a heat pump? Because you guys got tens of thousands of installations on your booster systems for refrigeration, but now going to heat pumps, there are some differences when you're going to do a startup. Is that correct?
There are differences, but basically it is same, because it's still a refrigeration cycle you have to make working. Yep. So all the basic stuff are the same. You still have compressors, you still have valves, you have gauges and instruments and control equipment. That is all same, but it's just how we use them. And for heat pumps, we also usually nowadays you have a lot of external equipments that we are not in control of. It could be for a water-to-water heat pump. We don't have control of the complete water circuit. So in that case, we rely on other contractors to have their things in order and up and working. And yeah, so that's just a lot of layers in it. But basically, it is to be treated as a big refrigeration unit. It's just a multi-megawatt unit. So it's just a big unit, but basically the same as we used to.
Yeah, and that's the thing, right? It's just when we get into these industrial heat pumps or large commercial heat pumps, because when I talk with people who do like commercial and then they talk about a rack, it's like, oh, it's so big, it's like almost industrial. But then you go into the industrial, it's just big. It's just more cooling or more heating that we're doing. And it's just, so you got bigger compressors, you got bigger valves, you got bigger vessels, but refrigeration, when we come back, it's doing all the same thing.
It's doing the same thing, yeah. So there's all the safety functions, all the basic how you load your compressors and all that stuff is basically the same. There's no difference. So if you know your groundwork, it's not a big step to go into heat pumps.
Yeah, but that's the thing are you as a technician or a contractor getting in CO2? It's no different than what you were installing for the last 20 years. Those processes need to be the same. You're pulling an evacuation down below 200 microns, making sure you pressure test everything by your codes and standards, making sure you test all the inputs and outputs. And we're going to talk about this stuff here going on, but we want to dive into some of the stories that Erik has and some of the systems that he's already worked on with contractors on how to start up. Because I've worked and talked with so many people from Advanced. I do tons of training on Advanced equipment, because if you follow their processes, it's like all the other manufacturers as well. They send you guides, like me and Eric were talking about earlier. Here's a step-by-step guide on if you do check 1, check 2, check 3, check 4, and you do all those checks before they come, if they're hired to come in to do the startup with you or hired a startup assist, and all those checks are done, that startup's going to go super smooth.
Exactly. So we try to make it as easy as possible for the installers, because we don't want to spend a lot of time on the phone with installers asking questions. We can answer the same questions a million times. It's so much easier to just state it in a manual in an easy readable way and easy understandable. So just a step-by-step guide, so everybody with a basic understanding can do this. That's one of our goals in this, and that's also why we here at the factory do a lot of pre-checks on all the equipment. So every single rack coming out of here is thoroughly tested, and software is installed and set up, and every single sensor or valves or whatever have been tested that it actually works. So we are quite sure that when it get out there, it's gonna start.
The thing is, though, Eric, that doesn't matter if you guys do all the checks at the factory. My job as the startup technician or the startup contractor is to be able to do all those checks anyway. So I should,
yeah, sure.
You know what I mean? So when I get out to the field, it's great that you did the quality control and you did a check, but me as a startup or controls technician, if you're good at your job, you got to do all those checks anyway. That's the verification to make sure your customer at the end of the day has a system that's working and functioning properly. And the ones that I know, I work with a ton of technicians and contractors around the world. The ones, those control guys, and same with Eric, those control guys and startup technicians who follow the process and do it and make sure, no complaining. They just, if there's an issue, they call and let them know, okay, this valve is not working or this is an issue. It happens sometimes. But when they go through those checklists and they bang it all off, those systems always start up faster and they run and more reliable for the long term.
Exactly, and it's not a tool just to push away a responsibility or anything. It's more a tool for the technicians to follow when they do the startup, and also because it could be a guy who's been starting up several systems and he know how to start it up. Okay, I don't need to read this stuff anymore. But it could be that there's been a change in the system. It could be that there's some special equipment on his system. So it's always a good idea just to we technicians, we hate manuals, but sometimes it's really good to read that 3-4 pages of instructions on how to do this and make your own checks. Because one thing that we check it, as you say, is really good, but nobody knows what happened to the system from it leaves the factory until it's on site. It could be anything. It could be a broken sensor on the way. It could be a broken cable or something. So you need to be able to figure out what's going on here, what's how you test that everything is okay, and hopefully when we do the pre-testing, you have a minimum of test you have to do on site.
Yeah. So because you go to a lot of field starts, you were in New Zealand there a few months ago, and you had a big. This wasn't a heat pump one, but this was a big facility that you did. But what are the startup checks that you want those technicians to or the contractors to have already checked? What are some of the main ones when you get to the site? Because I talk with a lot of startup guys, and sometimes they get there and the contractor's not ready, and it's not always the technician or contractor's fault. Could be the GC. There was some delays. Could be the building itself not being built. But when you get to a site, what are some of those top things that you want to make sure that's already done before you get there?
Yeah, there's the top things are basically everything that is not mounted on the unit from factory. So that would be your gas coolers, for instance, or all your all your evaporators out in the system. All those things we don't have any control of. So in that case, the installer have to check everything. So I have to check that his gas cooler is actually working, the fans are working, all the sensors on the fans are mounted correctly. So your air temperature sensor is actually mounted in the airflow of the gas cooler, and it's not placed just next to the hot exhaust from some other equipment. Your return gas temperature is mounted correctly on return lines and insulated and protected from weather and all that stuff. So all these checks you need to do as installer on site. And unfortunately, the gas cooler is probably not really an exciting component. It's mostly just a box of fans, right? So it's super boring. It's maybe not super interesting. It's just something, it's always on the roof in the rain. So you don't, nobody likes that one. But it's super important that all these things also work before we can start the unit. Because if we have a faulty gas cooler and we try to start the rack, all kinds of weird things can happen. You could go into a gas loop. You can go in. You're gonna have.
Let's talk about that. You just mentioned a gas loop. That's a good one. Can you explain to everyone what that means to you?
Yeah, gas loop is basically when the hot gas in the system is just circulated from the compressor right through your gas cooler, right through your high pressure valve into your receiver, through the bypass valve again, and back to the compressors in an uncontrolled loop. So yeah, that's a quick explanation. The technical part of it is it can happen for instance, if your return gas sensor on your gas cooler, your drop leg sensor, has fallen off the pipe. It's just hanging, dangling there. Then you get into a situation where the air temperature sensor and the gas temperature sensor have the same value. So now the gas cooler controller thinks that the temperature is satisfied because I can't cool it anymore. So it stops the fans.
Yeah. That's huge right there. And that one there is the basic and the number one thing that you need to check. But I've talked to so many manufacturers out there where that's hanging off. It's not insulated. It's the wrong sensor. Like they're using a CPC sensor for a Danfoss controller or vice versa, like a PT1000. This is what caused issue, and that's in all their checklists. I've read a lot of manuals, CO2 manuals, and that's one of the biggest things. It's always highlighted and it's always in the manual. Like you got to make sure that's landed properly. So thanks for sharing that. So now that's more, and we're talking about the gas cooler on transcritical booster rack. Yeah. You don't have any control of that because that's getting landed by the contractor or the GC or whoever, and then the control guys are pulling that wire. So now when we talk about a CO2 heat pump, it's not the gas cooler, but now if it's a water to water, it's some sort of water supply, right? That you wouldn't have.
There is some kind of water supply. Yeah. It could be anything. It could be some heat transfer from a sewage water system, or it could be from a district heat system or whatever system, giving us a little bit of water with some energy in, and we can take that energy and push it up in pressure, and we can supply it again out in a higher temperature state, so we can use it for something useful, like heating your building, heating your city, whatever. And this is basically what's this heat pump thing is all about. It is the reuse of waste heat, because there's no point in just generating a lot of new heat with your gas burners or whatever if you already have a heat source, which is your only. And you can, for instance, for this lower picture here, you can see this. You have a big evaporator here or whatever it is, heat rejector of some kind, and you just eject all that heat directly to the air, and it could be maybe like 40 degrees cooling water coming back from whatever production, and that 40-degree water here contains quite a lot of energy and it's just waste. And instead of just blowing it away and having a furnace heat up your building, then we can take that heat with the heat pump and convert it into a higher state of energy, so a higher temperature of water, return it to the building and heat it up. And and we can do that for a very low cost, because every time we use 1 kilowatt for running the heat pump, we get somewhere between 2.5 and 3.5 kilowatts of heat out of it. So that's not a bad deal. But with today's gas prices and electricity prices, that's not a bad deal.
Yeah. The thing is, sorry there. The thing is that we've done this in refrigeration for years. We just had the condensers out, and they're out there now, just throwing all that heat away. We're just throwing it into the atmosphere. We're creating heat energy because we got to push that unit up over the condensing point, push it really high, and then we just reject the heat. So we pull the heat out of the product and reject it. Then we came in with heat reclaim, where you said earlier, we got heat recovery, heat reclaim. Now we heat up preheat water or preheat air in the building. But now even bigger than that, on bigger process, now we're using these heat pumps to actually take a lot of that heat and then heating these buildings. Because I'm seeing more and more of this happening with CO2, a full all-in-one system.
Yeah, so because then we're starting to integrate everything in one system. So we can, but this is just your standard heat pump system here. This one here is a water-to-water heat pump, and it can only generate heat. That's what it does. What it can do. It can only generate heat, and it's really good at it. So, but the next step from this is also to make a complete climate control system, as we call it. So we can not only produce heat for the building, but also produce chilled water for your air conditioning or process cooling or whatever you need from a single heat source. That's super smart. We have made this. Oh, this is a different system. We have made this beast of a thing. Yeah, it's a 12-meter long system, 2.5 meters wide. So it can just fit on the rear end of a semi truck, which is super handy. And this small guy here can produce 700 kilowatts of heat and 400 kilowatts of cooling from air to water system. So what you see here on the back with the fans on are not a gas cooler. That is evaporators.
Okay. Yeah.
So that's your heat source.
Okay. Yeah, it's your heat source, right? And you need that.
And you need a heat source of some kind. In this case here, we go for a air to water system. It could be just a big chilling unit you have as a heat source instead. It doesn't really matter. We just need some kind of heat source.
Yeah. And so now this is you in the factory, you guys work on this, you guys set it up, you design it, you check all the set points. I did some videos, so go check out on the LinkedIn. I've done some with Kenneth Madsen on talking about their ejectors that are inside here and stuff. But you guys make this is great. But the next step is getting it out to the field. And you guys got some of these out to the field. And then we talked about it in the summertime about the startup that you were on for the one in Latvia, was it? I can't remember.
Yeah, it was in Latvia, yeah.
Okay. And so now after it gets in the field, the contractor or the technician or that company goes and does the install. So the install would be hooking up to what? So they get this unit, it drops off onto a pad. And then what's the next steps for those contractors? Oh, you got a picture.
This is actually the unit we talked about.
Okay.
Yeah, the contractor he makes this platform here for the unit to stand on. It can be a bit hard to see, but yeah, we've got some machine shoes here, and there you have our skid on the top. So he makes this platform here, and this platform is quite important because you need some space underneath the unit. To draw in all the air, and also now in Latvia here you get a bit of snow, so in the winter time all of this would be filled up with snow. So we have to lift it quite a bit to have access to fresh air at all times. And all of this is also they're stuck in what you call it, a French drain underneath here to drain away all the water when you're defrosting the system, because as we talked about before, these are evaporators, and as every evaporator, they need to be defrosted from time to time. And there's only one way that water can go, that's down. And if you just have it on a concrete slab or something, you have water everywhere. So you need some kind of drainage. Okay. And that is also a contractor issue. So the contractor have to make the drainage and the platform here. And then basically just from over here, that is his water system coming in here. This is only a heat pump. There's no cooling on this guy here. So it's only a heat pump. So it just connects his two water lines, and there's some cable trays here for powering up the unit. And that is
how important
that's basically what he'd have to do.
So how important is that the power? It's like any system. We need the right amount of energy to energize this. So because I know I've seen heat pumps out there, not these ones for an example, but they're on generators and stuff. And I've seen systems like chillers on generators because they're in the middle of the nowhere sometimes. But that's so important to have the right power, because we're dealing with a lot of electronics Maybe not on this site, but have you ever seen any issues like that with power issues causing the electronics to act up?
We have seen that in some areas where they have not so stable energy sources. We have micro dropouts on the power, where you just have like milliseconds when you lose your power. That can mess up like any system more or less. So that's not really ideal. But of course, you can feed this system with a UPS system, so you have battery backup on everything. So that's got to be eliminating the system. Of course, we cannot make a UPS big enough for driving the compressors and stuff, but the control system will at least survive if you lose power for a short period.
Yeah. Okay. So that's great. So now the contractor got it. They built the stands, they built the French drain, they pulled the electrical, get the right power there, whatever the voltage is, depending on where you're at in the world, is going to be a different voltage. And then they get the supply in and the supply out of whatever the process is.
Yeah, that's basically it. And then what he has to do then is of course make sure that his supply water is balanced to the calculation for the unit. Because we have, of course, we have been quoting a system that can deliver so many kilowatts at these temperatures at this flow. So if you don't have the right flow, you don't have the right temperatures, that is quite difficult just to adjust everything into a working system, because everything has been dimensioned for the quoted values.
Yeah. So this is now different than if you're working on, say, refrigeration and supermarket systems versus, unless you do secondary systems like secondary pump systems, because now we're dealing with flow. Because now this is not anything to do with the manufacturer of the heat pump. Now we're dealing with flow. So there's circulation pumps or process pumps, whatever you want to call them. And if those process pumps are not supplying the right flow, that is going to change up the whole system dynamics. And you got to get into something like pump curves now and things like that. So is that some of the stuff that you're talking about, Erik, for the contractor?
That's something the contractor really have to check up on and be sure that all his equipment is also dimensioned correctly and also set up correctly, and we verify it. Usually they verify it because for measuring the overall COP, you have to measure the flow and differential temperatures anyway. So usually they have a metering device on it, so they can tell the flow, they can tell the temperature, and everything is this. If you are exporting your heat to a distributed system or something, there's always some money included also. So of course they are interested in knowing the correct energy flow in the system.
Yeah.
So that part of it is fairly easy to convince them that this has to be in order. But of course we see from time to time that we come up and there's a pump system is not really calibrated correctly, or it's maybe dimensioned correctly, so it's a wrong size of pump for the system. It's either way too big or way too small, and that creates some delays, of course.
Yeah.
Yeah.
I just finished the course too, because I'm not a hydronics guy, but I just finished a chiller chiller course, and then I had to learn how to do pump curves. And I've never done it before, and I might have done it years ago on secondary pump system, but it took me about 20 minutes and I learned how to do it. Like I can actually now check a pump curve and plot it on a graph. It's not that difficult. And there's lots of YouTube videos you can go out and look at. So if you get into an heat pump application, now we're dealing with some hydronics that we didn't do before. You got to learn, you got to get the pump. There's going to be a pump curve for that specific pump, depending on the ratings and the horsepower of it. And you got to plot on how many gallons per minute or whatever your units you're using, that it can move and flow that specific fluid or whatever the process is.
Exactly, and it's as this is usually not a part of the refrigeration installation. It's more like a plumber system. Then that is a cooperation between you as a reefer tech and the plumbers to make everything work. And so there's two different contractors we have to talk to each other now, and that can also cause some issues sometimes, because if there's something wrong in the system, it's definitely the other guy's problem, right? So,
and that's why you should know how to do it, right? You should just know how to do it anyway. So
then you need, because it's a really good idea for you as a technician, a refrigeration technician, if you have just some insight in how this fluid dynamics works. And then you can more or less eyeball if you're within range. You say, okay, the system here is okay, but there's something wrong with the temperature. There's something wrong with the flow here, because I can see my system is acting up okay, but there's something wrong over on this side here.
Yeah.
So it's another layer of knowledge you have to read up on. And as you said, it's a short course here. Yeah, after an hour or so, you're pretty good going.
Yeah. So you were at this startup, is that correct? At this site here, were you at this one?
Yeah, I was at this startup here. Yeah.
So you were at this one. So this was when you got there, it was already mounted like this. It had power to it. It had all the hookups.
It had power and hookups, everything. The only thing it was missing was the CO2 charge.
Okay.
So yeah. So when we come to site, of course we do all our checks ourselves, as you would do. We check that the software is working, all the sensors are still working. There's nothing, no loose part from transportation, and just everything is working as you would do on any other rack. And we do that, and then we're starting. Okay, we are ready to charge the CO2. We have checked oil levels okay. We have charged the oil. When you do the vacuum on the system, anyways, you charge with oil because that's just super easy.
Yeah.
To pull the oil with the vacuum. And then you're ready to charge.
Stop there, Erik. I like that. This is because I've learned this from Advancer, from watching the videos. You guys like to use a vacuum to pull the oil in. I was always used to pumping it in. I was at a site, a field startup a few months ago, and they were pumping it in. But do you want to explain why you like to use a vacuum to pull it into the system, the oil in?
Oh, it's super easy work because you have everything set up anyways. You have your vacuum pumps on the system anyways. You have pulled it down to a full vacuum. So now it's just a matter of connecting your oil hose to your oil bucket and open the valve, and then let time happen, and then it's just gonna suck everything in. You don't have to lift a finger or anything. Just have to monitor the levels. And
that's huge, because now that saves time. And plus, you're still pulling the vacuum, because if you break the vacuum or you add 150 psi or 10 bar of CO2 and then add it, well, then you got to still pull a vacuum again. You got to go back and pull a vacuum on that receiver or that oil reservoir. So this actually can save time, and it's not that difficult to do. So
it's not that difficult, and I really like to just for making some extra security for myself. Then I isolate the oil vessel. So I close all the valves in and out and connect. So I have the vacuum pump directly on the vessel. So if I break the vacuum, because maybe the bucket runs dry and you suck in air, it's only a really small volume you have to re-evacuate.
Yeah,
that saves me a lot of time. And if you're two guys on site or something, one guy can do that and another guy can do the final checkup, so you don't waste any time. That's just a matter of being more efficient.
Yeah.
So when you don't,
yeah. So you get the oil in, and because you're at the startup, you're pulling a vacuum, you get the oil. What's the next step that you're working with a contractor or technician with?
Yeah, then we break the vacuum with CO2. So we make sure that all the systems are open and equalized in vacuum, and then we charge it with CO2 in gas form and vapor form only. Because if you just charge with liquid directly into the system at vacuum, you get dry ice immediately, and it's just a pain to get rid of again. So we give it, usually we charge it to about something between 7 and 10 bars of vapor pressure. That would be 100 psi-ish or something, of vapor pressure. When that is done, we start filling in liquid. Just on a normal supermarket system, we charge directly into the receiver, because then we have the whole refrigeration system to help us keep the pressure low if it's getting too high. That's super easy. On this system here, we found that it's a good idea to start with the receiver, fill up the receiver, fill up the liquid lines. The volumes are not that big because it's all the machine room is here. All the refrigeration system is basically only in here and in the feed lines out here. So it's a very small pipe volume you have in this system here. So it's quite easy to fill that up. But then we found as soon as you got liquid enough to run the unit, then it's easier to charge from your liquid line. So you close your separation valve between your liquid receiver and your liquid line, and then connect somewhere after that with your CO2 hose, and charge with liquid that way, and just let the compressors do the work for you. That worked quite well in these the systems here.
So at that time, what you are, I'm assuming, watching the sight glass and the pressure in the receiver and the flash tank as you're charging it, because in the field sometimes you don't always know how much gas. You would know how much CO2 this system is going to take, but a lot of technicians may not know if it's doing it. So you're watching the pressure and the sight glasses on the flash tank receiver, or how are you doing?
Yeah, we always monitor the pressures and the levels. So as soon as we got a minimum level on the system, we're basically ready to begin start up system. But preferably, if you're more liquid you can get in the flash gas tank directly, the better, because you have a larger connection. It will go faster. Yeah. But at some point you get up to a pressure where you say, okay, now your bottles can't really keep up anymore, because now you are at same pressure as ambient temperature pressure will take you. Because when you got like let's say here it was like 20 odd degrees outside, then you have about 55, 60 bars in your bottles.
Yeah.
And as soon as you get the same pressure in your vessels, you don't have any dry pressure in your bottles anymore.
Yeah, no
flow. And then you go nowhere. And an issue here we see a lot of times is, okay, that the guys they're getting CO2 delivered the day before or something. It's got a truckload of bottles are coming, and they unload it, and it's outside all night. And you maybe the temperature dropping at night. You maybe only have 5 degrees at night or something, or maybe freezing sometimes in winter time. Then your CO2 bottles are frozen, solid.
Yeah. There's no movement of that. There's no movement.
No, there you got no pressure. It's absolutely next to impossible to get anything out of them. And then you have to go all these tricks of when you use the suction line, or you get your apprentice to hook the bottles until they get hot.
Exactly. So okay, you're out in the field and you get the right amount of charge in there. So what's the process of starting this up now? So you're getting CO2 in there, you're watching it. What's the next step?
Yeah, the next steps that we in this case with the heat pumps, we simply just start at a low capacity. We can control the capacity directly. So how much compressor capacity are you cutting in? So we start at a low levels just to make sure everything's working, and slowly get the system working, and and checking all your water temperatures and your evaporator temperatures and everything, that all the figures checks out. And you don't want to do this too fast, because a water circuit is a really slow system, and the whole balance, the control system here, just to balance itself, is set to be really, really slow in order to catch those small fluctuations in temperature you will get. So just because you're raising your return temperature by your water temperature, your incoming water line here, if you raise that by a Kelvin or something, it's not gonna start the whole system at once, just cut in all the compressors and full load on the system, because that would create a lot of instability. So we have to go really, really slowly here. It's the best we do in hand mode. Just set the system in hand mode and just slowly work it up and check if everything is okay. And as more capacity is added, you also need to charge more CO2, because your evaporators will be more and more flooded. So fill up your evaporators, and so it's a waiting game. So you have to fill it up a bit, wait to see what happens, fill it up again, check some more, fill it up again, and you do this over a course of an hour or something. And then this system here we started up we got power on it until we had a running system. We still have some fine tuning, of course. It was about 2.5 hours.
Yeah. But that was after everything was checked and everything, verified. Temperature probe, pressure temperature, because startups can go really fast, because I've heard people, it's a 2 hour, just like you, a 2 hour startup. But if you didn't do all the pre-work, the evacuation, the oil, the charging, that takes time, you know, to
It
put them.
just takes a long time. Yeah. So well, just for the evacuation, we recommend you evacuate the system for at least 24 hours.
That should be a
Uh,
minimum. It's really,
that should
if you
be
get there.
absolute minimum, and you should also break the vacuum with nitrogen a couple of times during that process. So at least 24 hours, 2 days are better.
Yeah,
So
exactly. Until you get that down to 100 microns or below, you know, really deep vacuum inside
really,
that
really
system.
deep vacuum here, and that's because we don't like moisture in our system, and it's only when you do the deep vacuum for a long time, and in this case here, it could be quite difficult because the unit is outside and is, we can't put it in a heated room, so water boils at I think it's 20 millibars or something at 20 degrees. So it's quite a good vacuum you have to go with a quite a high temperature. It's a room temperature
Yeah.
before you start boiling off water. And if you can't get that temperature, you have to do the vacuum for quite some time, and you have to rely on your motor heaters, crankcase heaters in your compressors to generate some heat for the system so we can boil off any moisture.
And you may have to tarp it off and hire a heater. Like I've seen this happen, you know, in the middle of the winter. Like they pull a vacuum engine, you get big tarps and you put it over a cover, and you get fire going, like heat
Yeah,
going in
so
there, big heaters blowing in on the unit to heat it up if it's so cold to pull the evacuation. You have to do that sometimes. You might not have done it before, but I've seen it where contractors had to do it. So it's thinking differently if you need to get it up and running faster, because it could take you weeks if you got water in the system. It could take you, if it's cold out, it could take you weeks to get the water out.
basically take you weeks, yeah, because you have quite a lot of volume in there, and if you have been unfortunately enough that you get water in a pipe from production where you cool the pipe down and it's not dried proper afterwards, and or some external installation that's been open pipes and moisture is getting in from overnight or something, yeah, then you have an issue with water in the system. It's a pain to get rid of.
So slow startup, that's any system anyway, any CO2 refrigeration system, or even a supermarket rack. We just got faster at doing it. You know, we're just used to working with the HFCs for years. You know, you got faster and faster. Now this is with CO2. Every system is a slow startup, right? You turn some systems on, make sure they're working good, go to some more systems. And it's the same with this. We don't want to just bang everything off. It'll run into more issues. So now that we get the system up and running, one thing that I learned about this at Chelventa, that you guys are using ejectors in this versus what we're used to using in a supermarket transcritical booster system, where we got a high pressure valve and a bypass valve. There is ejectors, don't get me wrong, you can use ejectors, and I've done lots of podcasts with Dan Foss. So go check them out on the YouTube channel. But in here, you're using some ejectors, and I think might have been Carell's single ejectors in one of these
That is
systems.
Carell single ejectors. Just hang on a second. I think I've got one here.
Yeah, I'd love to see it. And maybe we can explain how it's working in this system. Because we know, like I said, go check out the Dan Foss videos they did with Patrick Clarity. Great guy, super smart. They have multi ejectors, where now Carell ejectors, I think they're licensed from Carrier. So, but these ejectors are single ejectors, and there's multiple manufacturers who make single ejectors out here. This is just one brand.
Yeah, this is quite a beast. So it's quite a beast. It's quite heavy, I tell you. It's made of brass, and it's massive. But basically, this is just a paint gun. Yeah, a
I
spray
like the way
gun.
you put that. It's
Yeah,
a spray gun. I
it's
like
just a
that.
spray gun. It's a quite simple system. I just keep it down here for now. So it's quite a simple system. It utilizes that you have your high pressure gas flow. You accelerate that over a small piece of pipe, exactly as you do with you have your high pressure on your spray gun, and you have a dipstick or dip pipe going into your paint bucket. And
Yep.
what really happens is when you take the high pressure gas, and then you push it into a chamber which is narrowing down, so you have like a funnel. And when you do this, yeah, according to physics, you have to conserve your momentum, and you can only do this when you're narrowing down your orifice, and you have to have the same amount of mass going through. You have to accelerate again, so you speed up the gas. So it's going about. I think it's gonna supersonic actually.
Wow.
Yeah.
Yep.
So and when you go this far, this fast over a small piece of pipe, you create a suction effect. You create a small vacuum of it. And this vacuum we are using, the dip tube you usually put into your paint bucket, we put that into our suction line from the evaporators. So now we are using the high pressure gas to lift the return gas, the pressure up to receiver pressure level. So all this gas coming from this guy here is pushed into your liquid receiver, and it's done without adding any kind of motor work or anything. You don't have a compressors, anything. You have a mechanical work from the high pressure gas, but that high pressure gas you have to slow down anyways, because you have to lower the pressure. So you have to take out the energies anyways with your high pressure valve. So this one here just replaces your high pressure valve, and we use it as a pump. So we pump. It basically replaces a compressor on your empty stage. Yeah. So we can simply take energy, use that energy from the high pressure gas to lift the suction pressure up to a receiver pressure level.
And that saves a huge amount of energy now. So we don't have such big compression ratio on those medium temp compressors. Now, if we can do that at a higher pressure.
Exactly. And on this system here, furthermore, we actually don't have any empty compressors on it. That sounds crazy. We only have parallel compression on it, because all the compressors are connected directly to the receiver tank.
So now, so now you're not pulling down to say 400 psi, 28 bar or whatever. We're not going down that low, or what we're going down. No, you're only going down to like 40 bar or 42 bar or whatever that range is. I don't know what it is, but
yeah, in that range, yeah, because in this case here we have a really high evaporation temperature from the evaporators. We are up at like +10, +15 in evaporation temperature, and so we don't have any need for this empty stage anymore, because we're not operating in that range anymore. We're operating at a very higher range. So if you look at the PI diagram where you have your MT and your ITs and your LT compressors, you will see on a PNI for this guy here, you will only have your IT, your parallel compressors. So that's a little bit of special way to do this, but it works really good.
But yeah, it does. And I know, because even 2 years ago when I was at Chilventa talking with you guys, and even all the other manufacturers in Europe that are using ejectors, a lot of people think here it's difficult to use in North America, but it all depends on the application. That you here in Canada, in a supermarket transcritical booster system, you don't need ejectors, like if you're just doing refrigeration. But when you're using a heat pump now here in Canada and district heat, ejectors might be the thing that you need on there, in this cold climate.
It's a definite tool in the box here. If we convert it into European waste, then up here in the north in Denmark, where I am, the ejectors are not that important for the system to function properly, because we have a reasonable cold climate. But as further south you get, to southern France, to Spain, to Portugal, to Greece, when you go into these kind of areas, then your high pressure gas will be so high pressure.
Yep.
that we are generating quite a bit of flash gas for your system. And in that case, we can use, instead of just generating flash gas for flash gas sake, we can use the ejectors here together with this high pressure, high volume, high pressure gas to lift the liquid from the empty stage to receiver pressure again, and again bypassing the compressor. So we're offloading the compressors, so we don't have to strain our compressors as much. We can maybe use less compressors on the system.
Yeah, and that's what it's all about. So we're trying to reduce the amount of work on these medium temp pressure compressors, right? We get less flash gas going in, because now before it gets to the compressors, we're taking it away. We're bringing it back.
Exactly. Yeah. So we're skipping a step. So we're just skipping that. We need to bleed off with the bypass valve a lot of flash gas into our empty compressors and just send them directly to the parallel compressors. So because that's a way shorter lift for the parallel compressors. Yeah.
Man, I could sit here and talk to you all day about this. So I got one last question for you. So for these high pressure valves, like everyone's like, these ejector valves, these single ejectors, like, oh, I don't know how it works. it is just an electronic valve. There's a motor on it. It's going to open and close the orifice to make it bigger, just like Erik said, to shoot out. What is that going to be controlled? So in your heat pump, what is controlling that to open and close to say, okay, we need to do more lift, we need less lift? So if someone's going to go in and look at your controls, if it's a Danfoss or Carell or whoever it is, doesn't matter. What is controlling that ejector for your system to make it most optimal, to make sure that it's always running at the best COP?
Yeah, that would be your for your refrigeration systems. That would be a parallel system to your high pressure valve. So as soon as the system sees that we have flash gas enough for running the IT compressors, then we start up the IT compressors, and when we shut the high pressure valve, and then we can start using the ejectors here at full effect, because now we can remove all that flash gas we are getting from the ejectors, but we also lift all this liquid from the low stages, and thereby we can maybe stop one or two of the empty compressors. So that's always a balance between your mass flows in the system. So it's a mass flows that dictate what kind of equipment we can start and stop.
And is it the same? So, and that was a CO2 system. Is that the same in here? It's the same with this one, how that one's working in the heat pump?
These guys here basically work as your empty compressors in this system here. So they would try to control the pressures in the system, and the compressors would just evacuate the flash tank. So basically they, in this kind of system here, they replace the compressor functions. So,
Okay.
and these work on a totally different concept. This is our own software that's working these guys. And so I'm not 100% into how that software really works at the moment, but we just trying to optimize all the processes at once on this system here with our own software. Because the standard, if you just go out and board yourself your standard Danfoss controller, Carell controller, it can do a lot of things. It's really good, and it can also be used for heat pumps. But when we use it for this kind of system here, it is lacking some functions, some special functions. So we have to redesign everything and come up with our own software for it. And
so I would think it would be taking the inlet and outlet water temperatures, how that is affected, right? Because now that compressor, like, we're going to have to change capacity. So depending on what my inlet water temperature is, will depend on how I need to run. And depending on my outlet water temperature, how much heat are we pulling out, or how much heat that we need.
Yeah, exactly. So it is controlled by the water temperature, because the customer is buying a water temperature at a given flow. So many kilowatts at this temperature. So as soon as we're not following that, of course we have to ramp up the system here, and again, if it gets too hot, we have to slow it down a bit. So we have to get a balance of everything. So that's a combination between the evaporators, how hard we are running the evaporators, and how hard we are running the ejectors and the compressors. So it's a little bit complex system. And maybe a video for itself.
No, definitely, man. This has been awesome, Erik. Like, I've learned a lot already. And I, like I said, we've talked for hours. We sat for lunch back in August for a couple hours just talking about it. And it's so fascinating to me, refrigeration, how it's evolving, because now you are working on, say, CO2 supermarket racks or commercial racks, but now you're getting into an industrial. You're going to have a lot more things to work on with CO2. So it's growing your knowledge, increasing. How can people find out more about you, Erik, or Advancer if they want to learn more?
Yeah, if you want to learn about what we do, we have our website, advancer.com, where you can see a lot of case stories about the things we do. We also attend, as you do here, webinars about different subjects. It could be about dimensioning heat pumps. It could be about heat reclaim systems. It could be about industrial applications or whatever. And you can find all that in our homepage under training, and you can sign up for these classes here. And also, like you do, you have special classes we have a whole series of online technical trainings you can sign up for. So you start from, you have I think it's about an hour videos where you dive into a specific topic on each video. And I think there's about 12 subjects or something, I think it is. And they always update it. So they're always coming out with new ones. So yeah. And of course, everything's for free.
Yeah. So definitely check it out. This is important. Continue to learn, continue to grow your knowledge, because you're just sitting here once or listening once on the podcast or watching this on the YouTube video. It's great, but you got to see it, do it, and, get out there, actually go out into the field and put your gauges on some of the stuff and your meters on it, and then read and learn and continue to grow your knowledge. Invest in yourself. That's how you're going to get better. That's how you're going to grow. Erik, thank you so much for hanging out at the CO2 Experts, and I look forward to chatting with you again.